Hi, my name is Aditya Rastogi, and I'm a software engineer in the Windows Developer and Experiences Platform team. I'm joined today by Sergio Pedri and Daniel Paulino from the Microsoft Store team. Performance is one of the pillars to building a fantastic Windows application, and so our hope is that you will leave this talk with a framework for how to investigate and think about performance, some suggestions on how you can maintain a performance-oriented mindset when working on your own apps, and even see some of these concepts in action through performance improvements made by Sergio and Daniel in the course of their work on the Microsoft Store application. Let's dive in. I want to first start by talking about these two fundamental questions. What is performance, and why is it important? One framing of this is to consider performance as a way of assessing how well an application does the job you've designed it to do, using the system resources at its disposal. Usually this translates into costs. How long does a particular operation take? How many CPU cycles does it use? How much memory does it take? These types of questions are distinctly quantitative and are related to the device where the application is running. However, performance has a distinctly qualitative side to it as well. It's the user's perception of how fast, smooth, and responsive your application is. You can likely recall the frustration you may have experienced while interacting with an application that has a jerky frame rate, or which seems to burn your device's battery when you use it. Or maybe the app is doing some long-running operation and doesn't signal this to you, resulting in confusion and the perception that the app is hung. As a developer, by keeping performance in mind, you can ensure that your users don't feel this type of frustration, and that your application is making efficient use of the user's system resources. These are great reasons to care about performance and to make time for it as you are working on your applications. So, how can one get started? What follows is an example framework for how to help guide your performance efforts, and it consists of a few different pieces. Identifying the problem and motivation for your effort, defining goals, and doing experiments. A key initial principle to guide your efforts is to think about the context around what you are doing. In fact, it is difficult to talk about performance without this. For example, are you trying to optimize an important user scenario that is critical to your application, such as how long it takes to launch? Are you doing more of an exploratory investigation based on reviewing code in your application and opportunistically improving something? Is there a performance issue that a customer has reported to you? The way you might approach the problem in each of these cases may differ. So being clear on the problem and its relative importance will help guide your next actions and keep your investigation focused. It's tempting to dive right into your code base and start making changes. However, you can save yourself a lot of time by doing a bit of upfront planning. Once you have an idea of the problem, figure out what you want to accomplish with your effort. In the case of a well-defined scenario, you can perhaps set explicit targets. For example, launching in under a certain number of seconds or consuming no more than a particular memory footprint on more modest hardware. In some cases, you may not even know the exact outcome you're trying to achieve. And this is okay. Performance investigations tend to be iterative, and your goals may change based on what you learn in each attempt. Within a given investigation, there may be a specific metric that you're looking at. Perhaps you're looking at the wall clock time of a user scenario that is taking too long and trying to reduce that value. For this case, there are useful ranges of time called interaction classes that help put boundaries around how long such operations can take. Downloading a file from the internet has a different user expectation in comparison to resizing the application window, which should feel virtually instantaneous. Maybe the property which is interesting for you is consumption of CPU or memory, and still other dimensions like power consumption, storage, or animation smoothness may be the item of interest. Taking note of the area of performance may help focus your investigation and guide how you want to measure and test any changes you end up making. Measurement and testing are core to performance work, which I've grouped together here under the topic of experimentation. A colleague of mine, David McCodge, analogizes this process to the scientific method, which I've found to be a useful thinking tool for structuring your approach. In the same manner of conducting a scientific experiment, you pose a hypothesis about your problem and attempt to prove or disprove it by making a change, measuring its effect, and comparing it against a baseline to see what effect it had. What you learn from that experiment will create new hypotheses to test and validate. When you are testing changes in practice, it is usually helpful to have a consistent environment, using automation where possible to guide your trials, and simulating whatever conditions are necessary for your investigation. For example, if you're trying to assess how your application performs on a loaded system, you might decide to have other artificial processes running in the background using up CPU. There are a variety of different tools available across the Windows application ecosystem to guide you in taking measurements and analyzing data from your test environment. I've noted a few of the Microsoft-provided offerings here, and for this set, there are great resources available at aka.ms choose perf tools to help you identify the appropriate tool for your case. The framework we just discussed is useful when you are about to embark on an investigation. But outside of that context, there are things you can do throughout the development lifecycle as guiding principles to help maintain a performance mindset. The first principle is something my department's director is fond of calling the Zen of performance, namely that the fastest code is the code that you don't run. It makes sense intuitively, and from a practical standpoint, the way to interpret this is to ask if a specific task needs to be done now, and if not, to defer that work until closer to when it's needed. This is a very useful principle, and keeping it in mind often helps prevent performance issues from being introduced in the first place. The next principle to keep in mind is that the operating system is a shared resource. So, exhibit good citizenship. In the foreground, it is often fine to consume extra memory or CPU to help the user get a particular job done. But when the user puts your application in the background, make sure that you give back the resources that you don't need. Keep your app's on-disk footprint and binary size lean, as this will help your application load faster. And finally, make sure you know what your most important app scenarios and code paths are. These are often good places to start in terms of where you may want to spend your optimization time. Automation can help preserve any gains you've made to these critical areas of your application. The concepts we've discussed hopefully give some food for thought regardless of where you are on your performance journey. To help make some of these ideas more concrete, it will be helpful to see some examples. I'll now pass along to Sergio, who will be illustrating some of these ideas in the context of the Microsoft Store application.
Thank you, Aditya. So to start diving into some examples of where we did some performance work for the Microsoft Store, first we want to showcase a kind of high-level optimization, which can sometimes require quite a lot of work to enable, but I can give you very noticeable improvements in return, and that is streaming. This also ties back to Aditya's point about apps being good OS citizens by reducing their disk usage. So first, what is streaming? So put simply, streaming is a process that lets the compiler remove all code that's determined to be unreferenced by your application, as well as all the metadata that's not needed. This can result in huge wins in binary size, as normal applications traditionally bundle a lot of code that's not really needed at runtime. But there is a catch. Enabling streaming, especially in applications that haven't really been written with support for this in mind, can be quite challenging. An example of this is reflection, which is super handy, extremely common, but unfortunately terrible for streaming, as there's lots of scenarios where these APIs are used that make it impossible for the runtime to know in advance what code or which member will be used at runtime, and therefore what code is safe to remove and what isn't. In these cases, a lot of work might be needed to refactor these parts, which is why it's incredibly important to always keep performance in mind while writing code, as doing so will likely just naturally lead you down a path that will also happen to be more linker-friendly and make the transition easier down the line. So here's a size comparison from an upcoming version of the store, which will have streaming enabled. So this required extensive work to refactor all code paths that were heavily relying on reflection, but the whole package is now 20 megabytes smaller. This means that we could remove 25% of the entire binary just thanks to this. And again, this also means that we get faster startup, especially on low-end devices that have lower disk speeds, and also faster updates, as there are just less data to download and to update when bumping the version of your app. Now, changing topics, we will look at a completely different approach that we also use to improve the performance of the store, but this time by reinventing a fundamental building block that many of our view models and services use, while also adopting a performance-oriented mindset while creating this new API. Specifically, we will go over how we reworked our APIs to dispatch code to the UI thread to both make them faster, reduce allocations, and also make the usability much better. We felt this was a good example to show how, if you spend enough time designing APIs and thinking about how to solve problems with performance in mind, you often won't have to make sacrifices in either performance or usability. And instead, you'll be able to get pretty good results on both fronts. So first, let's start with an overview of what this change is about, dispatching to and away from the UI thread. Now, of course, we all want to keep the UI of our applications as responsive as possible, which means executing expensive work off the UI thread and then only getting back to it when it's needed. So for instance, to update some UI component that can only be accessed from the UI thread. Now, on your UWP and WinUI3 applications, the way you dispatch to the UI thread is by using dispatcher queue, try, and queue. And you can see here a snippet that shows some method in a view model that queues some work. So it first notifies the UI that work is starting, then queues some work on the thread pool, and then once that's done, it dispatches back to the UI thread to show the results. These are several issues. It causes several closures and delegates to be allocated. It potentially does unnecessary dispatches. So for instance, if the method happens to be invoked while already on the UI thread. And lastly, it's also just quite verbose and hard to read. Now, you could certainly improve things a bit here with some helpers. So for instance, by taking a function to execute on the UI thread and then wrapping that with a task completion source that the caller can await. That would improve things a bit, but you would still end up with nested callbacks, and then with an even more inefficient solution, as now you would be allocating yet another closure and delegate for the wrapping method, plus the task completion source itself. So before diving into the technical implementation, I wanted to give some context and show a couple of examples of where similar patterns are actually used in the Microsoft Store. Dispatching to the UI thread is a very common operation that's done extensively throughout the code base, but I wanted to show two cases where this back and forth is very apparent, and that's when reporting progress when installing or updating apps. So you can see here that as apps are installed or updated, the installer will do some work on the background thread, and then we will often have to go back to the UI thread to then inform the user about this ongoing work. So for instance, to display the current install percentage. You can see this in action in the product page on the left and on the library on the right. So how can we actually improve things here? There are actually two different components to consider. So first, there's the implementation tackling the main source of overhead from dispatcher queue, try, and queue. And then there's the abstraction built on top of this to let consumers benefit from the performance improvements while also getting a more user-friendly API surface. So for the former, the issue lied in the way the callbacks were dispatched to native code. So we had the allocation of a closure for each callback, then the allocation of a delegate, and then the runtime had to allocate some kind of wrapping object implementing a native API to pass this state down to the underlying WinRT APIs doing the work. So to solve this, we implemented the native iDispatcherQueue callback interface manually through a struct type. So you can see here we're manually populating the virtual method table for this type, pointing to our own methods. And we're also using GC handles to track this state without additional managed allocations. And now, since this is a fully native object, we can then also pass it down directly to the underlying WinRT APIs, which will then use it to run our callbacks. The screenshot you can see here is from the WinUI 3 implementation that we're open sourcing, and you can also see many of the cool new C# and .NET features at play, such as function pointers and the unmanaged callers only attribute, which lets us take the address of a method with an unmanaged calling convention and then directly pass it to a native API. The implementation in the store is slightly different since it's using GWP. So for instance, we have to use Marshall get function pointer for delegate, but that doesn't really affect the performance aspect of this. So here you're seeing the modern version that will then be in WinApp SDK as well. And here instead, you can see a fragment of code that's then plumbing all of this low-level implementation through the ValueTask infrastructure. Specifically, we wrote a custom awaiter type that implements IValueTaskSource, meaning that we can then expose a ValueTask returning API to our view models, so they don't even need to know about dispatcher queue at all, which makes the whole thing even more modular. And here you can see what the same snippet from earlier looks like, but updated to use the new APIs. So the whole method is now asynchronous, and we're just using a way to easily shift between different execution contexts. This results in better performance, as the compiler will just use a single async state machine for the whole method, and will no longer incur a delegate allocation and a closure allocation for every single callback. Additionally, unnecessary dispatches are also automatically skipped. And then finally, the code is just so much easier to read as well. So we no longer have nested callbacks with multiple indentations, and instead everything is in line and using the same async await pattern that we all know and love. And as a nice bonus, making the method asynchronous also means that exceptions will no longer just crash the whole app, but instead they will either be caught from callers awaiting them, or they will bubble up to the task scheduler unobserved task exception event, so that we can also log all of them from a single place instead of having to sprinkle additional logging calls all over the code base, which would then add even more verbosity and overhead. So finally, here's the benchmark results showing some performance numbers for this new low-level building block that the API is built upon. So not only we got some nice performance improvements, but we also made it completely allocation-free, which can help reduce GC pause times. And of course, we then have our nice abstraction on top of this to then give developers a more user-friendly API to use. This is all to say, if you really keep performance in mind while designing APIs, you can often make things better without necessarily having to give up on usability just for the sake of performance. And with that, I will now pass it on to Daniel, who will show you how you can leverage animations to make your app feel faster.
Thanks, Sergio. Hey, everyone. I'm Daniel, and I'm also an engineer on the Microsoft Store team. We're now going to move from a quantitative perspective to a more qualitative perspective of performance. Specifically, I want to show you how we use high-performance animations in the Microsoft Store. Several years ago, Windows released a new animations API called Composition APIs. These were designed from the ground up to run on an independent non-UI thread. This ensures that your app's UI remains responsive, even when performing heavy work or advanced animations. This goes back to what Aditya said regarding keeping UI responsive as a core part of having a performance mindset. Plus, these animations are GPU accelerated and run at 60 frames per second or higher. Altogether, composition animations allow you to build advanced UI that remains performant and buttery smooth. For us in the store team, we use animations in a few ways. First, we use it to soften transitions. In this GIF, you could see that when we click on the Xbox icon, it transitions to the next page with a connected animation. This preserves the user's context and smoothens the transition from home page to the product page. Second, animations add delight to user interactions, like if you're scrolling on the page or clicking on a button. Third, we use animations to improve the perception of performance in the store, such as when waiting for some data to load on a page. Now, let's drill into a few more examples in the store. One animation we use is parallax. For this one, users can scroll down on a page and some content will scroll at the same rate. Meanwhile, an image in the background scrolls at a slower rate. This adds depth to the store, and it adds a bit of delight when scrolling. Because this uses composition animations, it runs smoothly at 60 frames per second or higher. Next, we use spring physics. These are animations that are provided by the Composition API. You could see in this GIF that we have a list of icons that are loaded on the page. As the icons appear, there's a small spring in their steps. Once again, this animation adds delight. The third animation is morph. This one is extra special since our teammate Chow Chow created these using Composition APIs. And as of this recording, he has an open pull request adding this to the Windows Community Toolkit so that all developers will be able to use it. On this page, you can see that we have a top module called the buy box. It morphs into a floating bar on the top of the page as you scroll down. This uses composition to animate one UI element into another. Because all of these animations use composition, our store remains responsive and users have an elevated experience as they browse our app. So let's show you a demo of how to add animations to your app. For this example, it's based on a scenario that happened to the store. We had a module that was slow at loading. Without animations, it was jarring to the user. Using the performance guidance Aditya mentioned, we identified this as a problem. We experimented with some animations, and we kept iterating until we reached our goals. The result is a module that fades in smoothly and without the feeling of lag. Let's apply the same mental framework for the demo. Here I have a native LinkedIn-style app. Essentially, it's an app that displays my professional profile, showing some information about me and the personal projects I've worked on. I'm going to start the app, and I want you to see the loading experience. You can see that one of the images loads a couple seconds later. This is jarring, and your customers may think, oh, there was a lag. Because in one frame, there was no image, and in the next frame, the image suddenly appears. So let's try to smooth this out with implicit animations from the Windows Community Toolkit. Jumping to the codebase, I'm going to uncomment some code. Here, I've added 2 implicit animations from the Windows Community Toolkit. These can be added just using XAML, and under the hood, it uses composition animations, and it triggers when visibility properties change. The opacity animation will fade the image in with a duration of 2 seconds. The translation animation will move the image from a starting position to a final position, also with a duration of 2 seconds. Now let's test our changes. Okay, so it looks a bit better. The image fades in with a slight translation animation. It's not as jarring as before, but I'm still not satisfied. I think there's still a perception of lag here. Upon closer inspection, you'll notice that the module underneath the image changes positions in a flash. Let's try fixing that. Hopping back to the code, we're going to add a third type of animation called offset animation. I'm going to add these as attached properties to the elements below the slow image. Now I want to show you what the static resource is. As you can see, it's just a single line of code that says offset animations. This is also an implicit animation from the toolkit, but these will trigger anytime an object changes its position instead of triggering based on visibility. So let's try this out again. Now what you'll see is a buttery smooth animation that fades the image in, and the module content underneath literally moves and makes space for that image. The combined effect changes the game for your app. Instead of users feeling parts of your UI is laggy, they almost feel as though these delays are by design because of the smooth and carefully crafted entrance animation for the content. Overall, users perceive your app as smooth and performant, even if the delay is identical. That was a quick demo on how to apply Aditya's performance guidance to a problem and finding a solution using animations. I also want to emphasize that implicit animations are easy to get started with. They're open source, and they're available from the Windows Community Toolkit. If you haven't tried them out yet, check them out today. To close, users today demand performant apps with smooth experiences. It's important to keep UI responsive and improve the perception of performance, and composition animations are an integral part of that. And with that, I'll pass it back to Aditya.
Thank you, Daniel and Sergio. Performance is a very broad and deep topic, but hopefully this talk has given you some ideas for your own projects and applications, and shown you examples of how engineers at Microsoft apply these same conceptual frameworks and ideas. We have a great set of content available at aka.ms/winappperf to help you in your performance efforts, including additional guidance and links to tools. We've also included some additional URLs here where you can learn more about the technologies used in the examples you just watched. We hope that these resources can help you in building fast, efficient software that your users will love.